move from not only observations, but to something called quantum cosmology, applying the theories of quantum physics to the universe. Now, at first blush, that seems absurd because quantum mechanics deals with the smallest particles that exist, and the universe is the largest structure that we have. So how do you combine them, and why is quantum cosmology now so important?
The universe is big now, but it was pretty small before. At its beginnings, it was something like 10 to the minus 43 centimeters.
So that's the so-called Planck length, which is the smallest imaginable. Now, how do you know that?
Well, we study our universe through two cherished theories: quantum theory and the theory of general relativity, which is really a theory of gravitation. And in general relativity, you have this constant, Newton's constant, that tells us about the strength of gravity. Inverse of that gives us the Planck length, and that's where that number comes about. How do we know that the universe was that small earlier on? Is simply by tracing backwards the evolution. We know
it's expanding now, so we run the movie backwards.
Exactly, okay. and we also know the ingredients that this universe contains, because the growth of the universe is determined whether it's filled up with matter or radiation or energy or whatnot. Since we know the composition of the universe at every epoch, then we can trace to high accuracy its size very early on from the beginning. So since the universe started off very small, it means that quantum theory should apply to it. And that brings us head on with the big problem, and that is the friction, the continuing friction between the theory of general relativity and the quantum theory. There is no easy answer out of that conundrum yet. We do not have a theory of quantum gravity, but one of the candidates that at least allows us to talk of quantum gravity and do a calculation when that becomes necessary, such as the early universe, that theory is the theory of quantum cosmology. And Bryce DeWitt and John Wheeler were the two founding fathers of that theory. Quantum cosmology is attempting to describe the universe as a quantum wave function, but it's also attempting to do so when the force of gravity is extremely important. And that's why we look at that theory as a quantum gravity theory of the universe.
So normally the quantum wave function defined by the Schrodinger equation is for very, very small things in which gravity has no significance, because the order of magnitude of gravity, although gravity exists, is so minusculely small in comparison, right?
Yeah. But back then the force of gravity was extremely important, and quantum cosmology is studying the universe when space-time does not exist yet. So it operates on an abstract space given by the three geometries of these quantum particles that will become universes, and given by whatever fields and quantum particles these objects will contain. It's a timeless equation, in the sense that it gives us a set of initial states of what will become universes, but it is limited by this problem that it constrains us to a timeless evolution of the universe.
What does that mean? Because quantum, in general, is a development over time.
Yeah, it's an assumption of the theory that says that the total energy of the system, including the gravitational energy given by the geometry, and all the particle content, the sum of all those objects should add up to zero.
Because gravity is you have the mass and then a negative.
So yeah, the sum of the gravitational Hamiltonian plus the quantum field Hamiltonian should add up.
Which is the total energy of the system.
Exactly. Acting on the wave function of the universe, that should be equal to zero.
So
now, normally the Schrodinger equation says that the sum of all the energies acting on the wave function should be equal to the time evolution, is the time derivative.
Right.
In this case, it's equal to zero. So it limits that evolution.
And so that is a fantastic assumption that you don't have to create energy, matter, energy, because it's zero, but you have two different kinds of expressions. One's a negative, one's a positive, and together they're zero. So theoretically, a zero can just emerge out of nothing.
Yeah,
Is that
that's exactly right. Yeah.
yeah, that seems pretty incredible, don't you think?
It's and it also opens a can of worms, and that's why quantum cosmology has been the object of so much criticism and discussion and debate, because again it takes us back to the question, what is time? What does it mean to have a timeless entity? And it tells us about the state of the universe at one particular moment, at time equals zero, at the very beginning, but it makes it hard for us to follow what was there before.
So just looking at the overview, what are the kinds of questions, theoretically, can quantum cosmology answer?
Well, it can answer quite a lot of questions as long as we are aware that there are these still unexplored issues, such as the concept of time and many other subtleties that quantum cosmology contains. But for example, I used it in my theory. I use quantum cosmology to exactly be able to address the question of the probability. What's the chance that our universe could start at high energy inflation, and what else can happen at those energies? And the only way to do that, at that regime, general relativity breaks down. So we need a quantum theory of gravity, and at present the only working theory we have is quantum cosmology. So.
Carlo, one of the pinnacles of human achievement is being able to unify the understanding of the most small in quantum theory with the most large, which is the origins and structure of the universe. As someone who works in quantum cosmology, what are your emotions and what are the kinds of things that you do?
My emotions is that is infinitely charming and a fascinating question. I mean, I'm infinitely attracted to it. I think it's important to separate problems, not to confuse problems. Quantum cosmology is a name which is a bit too vast. I think one separates three different problems, and one is quantum gravity. Quantum gravity by itself has nothing to do with cosmology. So quantum gravity is a problem. What are the quantum feature of space and time, or the gravitational field? We know the gravitational field is space-time. So what is the quantum property of that? So if I ask what happened to the center of a black hole, is going to black hole explode or whatever? If I happen, the space is granular, as I believe in loop quantum gravity, that would be fine. These are quantum aspect of space and time, of gravitational field, nothing to do with the cosmos. So that's one, it's quantum gravity. Number two is we see the universe expanding. We have this marvelous thing, which is scientific cosmology. It started by Einstein with all this observation. We see the universe accelerating. We realize there was a Big Bang. Fantastic. There's a dynamic of the big thing. This dynamic of the big thing needs quantum mechanics. Why? Because in the deep past there was probably quantum, so we need quantum gravity. So we need quantum gravity to understand the quantum aspect of large structure. And that's quantum cosmology 1. Quantum cosmology 2, which is a totally different thing, is how do I do the quantum theory of everything? But everything doesn't mean the universe at large, because what the cosmologist studies is the universe at large, which doesn't mean, for instance, you and I. You and I are not in the equation of the cosmologist. My little finger is not in the equation of the cosmologist. So cosmology is the study of large degrees of freedom of the universe. Quantum cosmology sometimes is used in the sense of understanding the quantum theory of everything, which would be a good problem even if the universe was not expanding, even if there was no Big Bang. And I think the quantum theory of everything is a premature problem. We don't have clear ideas about that. We're confused about quantum mechanics. We should not confuse the three problems. These are three very different problems.
But what is the unity in terms of the thinking that's brought to the three problems? It's obviously an understanding of the world in quantum terms. I mean, there's some basic thing underlying all three.
Yeah, we do believe that quantum mechanics is the basic theory of how things move, how things happen, how things change. So three things have happened. One is discovery of quantum mechanics, one is discovery of general relativity, and one is the beginning of the scientific study of the large scales. mechanics. Nobody thought really that it was possible before 1917 when Einstein published this incredible article, which is a fantastic article because it's one of the best Einstein articles and is full of mistakes. He says, obviously the universe is not expanding, and therefore this it was wrong. It was expanding. But he started the possibility of studying the large-scale structure of the universe. So three things: the large-scale structure of cosmos coming into our scientific domain, quantum mechanics, and general relativity, and each of these three has to be connected to the other, and none of this is very clear yet.
What is the wave function of the universe?
Exactly.
That sounds rather ambitious.
The wave function of the universe is the idea that is in the third leg. So, can we do the quantum theory of everything? You see, my own take on that is that we cannot, because I think physics, it's studying how one part of the universe affects another part of the universe. So you always have to take reality, split in two, and say, well, this is my observer, this is what he's observing, how this affects this one. So the wave function of the universe would be how the universe as a whole affects something outside. But something outside is nothing outside, right? I mean, maybe there's God, but it doesn't need us to do physics for him or her or whatever. So I don't think the wave function of the universe is a useful concept at all. I think we should do quantum physics of part of the universe, and the wave function is always the wave function of one piece of universe with respect to another piece of the universe. It tells how one part of the universe is going to affect another part of the universe. So quantum cosmology, in the sense of let's study the quantum feature of the Big Bang, it's good physical science. Quantum cosmology, in the sense of let's do the quantum theory of everything, I respect people trying to do that. I have wonderful colleagues who are trying to do that. But it might be that it's not the right project.
Andreas, I know something of quantum mechanics and a lot about cosmology, and quantum mechanics is of the very small, dealing with particles and fields at the most microscopic level, and cosmology is the study of the universe. In recent decade or two, the idea of quantum cosmology comes up. That sounds like an oxymoron, where you're dealing with the very smallest thing applied to the very largest. So how does this happen, and why are you a quantum cosmologist?
So maybe I'll start by trying to kind of reset your perspective a little bit. So as a physicist, I understand that quantum mechanics underlies everything. So we're all quantum, everything is quantum. And then the fact is that many of the features of quantum physics don't really show up in ordinary things. So this is a quantum bench, but we never have to use quantum mechanics to understand it. But you have to, we call it a bench is a classical object, you and I are classical objects. We have to earn that status. It's quantum is everywhere, and it's only certain things that can ignore it, basically. And so, of course it's a quantum universe. There's no question about that. But then, okay, so that's kind of a glib answer, but let's get a little deeper. So the answer that probably anyone at this conference would give is cosmic inflation. So one of the remarkable features of cosmic inflation is that it expands the universe very rapidly, and as it does so, it takes features that are way down at the tiny quantum level and just pushes them up to the biggest scales, so that actually according to cosmic inflation theory, every galaxy that we see was created out of a tiny quantum thing.
Which is an awesome concept.
Absolutely awesome. It's absolutely amazing. And so much so that it pushes, so we think we know the quantum nature of the elementary particles, but inflation is so fierce that it pushes the boundaries of that down to where we're not even sure we know the quantum nature of what's coming up from the quantum level. So it's a very exciting, very profound part of our studies.
What are some of the current issues that others and you are working on at the frontier of the field?
Well, one of the things that really fascinates me, I've been very curious about the possibility of a finite universe, and there's several reasons where modern sort of modern understandings of cosmology have allowed us to explore that possibility in a more concrete way. The dark energy, a whole other topic, but the dark energy has actually made it possible to think about a finite universe in more concrete terms than we ever have been able to do before. And that's something I've developed quite a bit. And one of the interesting features of that is that we may actually see in the universe around us the hints of the very beginning of inflation. So basically, most inflation theories have inflation run so long that we'll never see the beginning.
Right.
But in my theory, you actually can look back to the beginning because inflation's shorter than most people think it is. And
What do you define as short?
just long enough to create the universe around us. So
it doesn't have to be.
It's about 65 expansion times at the time. So it's just enough so that the very largest objects in our universe were maybe present right at the beginning of inflation, maybe a little before inflation, and we've done some modeling of that. And one of the fascinating things that's come out, and it's just come out in the paper where we just posted the preprint. We show that one of the ways we model that beginning, the sort of special features of the beginning of inflation, can show up in tiny little wiggles in the power spectrum of the microwave background. The microwave background is probably the most important data set in cosmology.
Right.
And the best data set we have, there's some sort of informal puzzlement about some of the small scale features. Is it noise? Is it physics? And we're starting to see this. We have a way with our theory of creating these kind of tiny fluctuations out of physics. And the project we're starting now that we know we can create them, the project we're starting now is to see, does the data actually match what we're predicting?
And what would be the implications of that if it does?
So the clear implication is that there would be a different initial state than people assume for inflation, and one that is motivated by the finite universe theory. So the clearest implication is something's different from what we thought about inflation, and then exactly what that is, we'll have to work harder on. But I'd have my favorite. I have an idea what that might be.
What are some other issues that are extant in quantum cosmology?
Well, there still remains. So even if you believe in inflation, there's the question of what went before, and we have, I would say, way too little to say about that. A lot rides on that. The arrow of time is an absolutely crucial question for cosmology. It absolutely does depend on what went before. What these quantum features look like that I was just talking about depends on what went before. So that's a wide open subject and very difficult one.
How do you attack what's gone before? What kind of imprint of what was before can be on what is now, since it went through the inflation and the Big Bang?
So that's there. So I guess one thing I should say is that a lot of this work is done based on the curiosity, and you hope it better have some imprint. But there are kinds of imprints you could have, and really in my theory, where there's a short amount of inflation, you are looking at what happened before. You're looking at the beginning of inflation. You're learning about what happened before. So it could be all these oscillations we see in the microwave background. Could be the tiny oscillations. Might be from that. Other things, people have a lot of different ideas about what went before, and some people have tried to make predictions. It's such a big, I think it's such a difficult theoretical problem that it's okay for people to struggle with the theory for a little bit without rushing to a conclusion about how you'd observe it. But it absolutely is crucial. I think for us to be satisfied as scientists, you really want to have some observable prediction when all is said and done. And we probably don't know where the next exciting thing is going to come from.
That's part of the excitement.
Absolutely, absolutely.
Jim, I really want to understand the Jim, I really want to understand the universe and the structure of reality, and I know I've got to deal with quantum mechanics, and for the very small, and I've got to deal with the general relativity for the entire universe. You've introduced the concept of the wave function of the universe, which I don't understand. I can't imagine how you can have a wave function, which I understand for subatomic particles, for the entire universe.
To understand what a wave function is, let's first begin with ordinary quantum mechanics.
Okay.
Right? If we have an isolated system, it has a quantum state, and it's described by a wave function. The universe, perforce, is an isolated system because there's nothing outside it. Therefore, we expect that it too should have an analogous quantum mechanics that has something in it which specifies the state of the system, which would be a wave function of the universe. So it's a very natural concept. The key difference is that most wave functions, ordinary, in, say, the theory of U, work in a background spacetime. Right? So the wave function changes with time. It describes how probabilities of where you sit, for example, would change in time. But this is supposed to be a wave function of spacetime, right? That includes all those degrees of freedom. And therefore, it isn't in any background. So the argument of the wave function contains the quantum gravitational degrees of freedom that, for appropriate wave functions, would describe classical spacetime and reduce to the ordinary notion of quantum state.
When you're saying about describe, what does describe mean? Does describe mean some general structure, or does describe mean the absolute history of every piece of foam that's floating on this river?
That's a matter of coarse graining, as it said.
Yes.
You can have a description that describes every piece of foam included in the wave function.
We
wouldn't know how to calculate that.
A superfine grain.
Right, superfine grain. So, but the universe is remarkably...
So conceptually, that in principle, you could do that.
That's right. In principle,
so
you could do
I mean, that's incomprehensible to me, because that would be the summation of 10 to the 90th particles in some kind of a probabilistic way over time, every Planck's second, or I mean, it just seems bizarre.
The moon is made up of a very large number of particles.
Yes.
If you want to describe, forget about space-time for the moment, if you want to describe the state of the moon, you could write down a wave function that would have 10 to the 40th degrees of freedom in it, right? And then that would describe the state of the moon. But we're not interested in the state of what every little atom is doing inside the moon. We're only interested typically in its motion. So you coarse grain, and you describe only the motion of the center of mass of the moon. And so you can write down a state that is a product of everything inside and the motion of the center of mass motion. Then you integrate out all those other degrees of freedom, and you just describe the motion of the moon.
Okay, so apply that way of thinking to the wave function of the universe. Where is it today? What can you do today? And what is the potential in the future?
There are different theories of the wave function of the universe. In quantum mechanics, if you have a wave function of some system and you don't know what it is, in principle, you could find it by replicating the conditions under which it was created, making a whole lot of measurements, and then you discover what the wave function is. That's not possible in cosmology because we can't replicate the universe, stand outside it, and count what's going on. So a wave function of the universe has to be part of the fundamental theory, what physicists sometimes call, Weinberg used to call the final theory, right, of everything. So today's final theories consist of two pieces: a theory of dynamics, evolution, like string theory, and a theory of the quantum state. And you can't get, if you don't have both, you don't have any predictions at all. People make predictions sometimes often, right, with assumptions, hidden assumptions about what the state is, but strictly speaking, you need both. My teacher, Gelman, used to describe this to me in the following way. He said it's like the I Ching, right? It's not enough just to have the book of changes, right? Meaning essentially, the wave function. You also need to pin the description of what the rest of what the alternatives are for the universe. We have both of those, and incorporating a notion of how the fundamental theory of how they evolve, then you get predictions for the whole thing.
Okay, I'm still not getting the point, the difference between the universe and an individual quantum system. With an individual quantum system, by fundamental definition, you have to take a measurement. There has to be an observer. It doesn't have to be sentient, but some kind of an observer through a measurement. And that's obviously impossible in the universe, because by definition, you're defining it as a closed system of the whole thing.
Let's forget about space-time degrees of freedom. Assume space-time is fixed. Then let's consider a universe that's just in a very large box, 20,000 megaparsecs on the side. All the particles and you, right? Everything is in the box.
Right.
Okay, that's described by some state. It doesn't have gravitational degrees of freedom by assumption, but it has the wave function as a function of all the positions of all those particles, and you can calculate what goes on in the box. What are the ripples in the river, if you like?
And that doesn't violate the fundamental principle of quantum mechanics.
Not as. Do you mean the uncertainty principle, perchance?
No, no. Just generally that you have to have a measurement, an independent interaction.
We have to have a form of quantum mechanics which is suitable for the problem.
Okay.
Okay. So it can't be obviously a quantum mechanics of measurements, right? It's a quantum mechanics of closed systems like this. And starting in with the work of Everett in 1957, we understand how to do that. Right. Without quantum mechanics, without measurements. Measurements can be described, but they're not fundamental to the theory.
Yeah, I'd just say the multi-world theory that came out of Everett is controversial, and I'm not necessarily a believer, but I understand the internal consistency of what it can do.
It's not controversial among cosmologists. What choice do they have?
Well, I would think that a lot of them would want any other choice other than this multiplicity of worlds, although maybe if you do it in a different style of alternative histories as opposed to actual worlds, that's a kind of a halfway house.
The multiplicity of worlds isn't fixed. We can discuss different levels of coarse graining, right? And there are different numbers of histories and different coarse graining descriptions. Let's just take, did you sit on this end or on this end? That's a history at a certain time. And that's represented in the theory.
I've been wondering about this.
So you don't have to have this multiplicity. In fact, it's impossible to have too much multiplicity, because then you need the histories not to interfere with one another. If they were too fine-grained, the decoherence, as it's called, would fail.
I've been worried about this one question. If I go with you on a wave function of the universe, what happens if there's a multiverse?
We would have a larger universe to apply quantum mechanics to. It depends on what you mean by multiverse, of course. But a typical...
an inflationary multiverse.
Yeah, okay. So it just means you have to deal with a very large...
But it doesn't perturb your overall approach.
No, in fact, we calculate in it, right, with it. I myself...
I'm relieved that you can deal with a multiverse.
But I have to tell you in confidence that every time we do one of those calculations, we use very simple models in which lots of degrees of freedom are just eliminated. Sometimes it's called mini superspace. And we calculate in those models and hope that as we extend the calculation to finer and finer grained situations, that the results of those calculations would be robust. That's how we make our daily bread, so to speak.
Don, we're here at another FQXI conference, and no matter what the overall topic, quantum cosmology always seems to be one of the sub-themes, because many of the people here are quantum physicists interested in cosmology, and of course many cosmologists are here too. As we apply the theories of the extremely small in quantum mechanics to the theories of the largest possible structures in the universe, what are some of the counterintuitive ideas that can come forth when we apply quantum mechanics to the whole universe?
Yes, well, normally we apply quantum mechanics to things that are very small, and the universe is very big, but we do believe that at least at some level of approximation, the universe was once much smaller than it is today. In fact, sufficiently small that quantum mechanics would have been important in it. And so if you take that into account, it's saying in some sense, just like in ordinary quantum mechanics, you can't have a definite position and definite momentum of a particle
at the same time.
At the same time, yeah. So if you measure one precisely, the other will be imprecise and so on. Then similarly in quantum cosmology, the size of the universe and its expansion rate cannot both be arbitrarily precise. Now, of course, the imprecision is extraordinarily tiny today compared to just our observational uncertainties as to how big the universe is and how fast it's expanding. But in the early universe, it appears like it may have more, more significance. And there could be, and we describe the universe in terms of a quantum state. And if we talk about the quantum state in some approximate sense as a superposition or a combination of different histories of the universe expanding, then we could say that in some crude sense it's roughly like an ensemble of different universes with different expansion rates and different sizes and so on. And it does seem that our universe underwent a long period of what's called inflation, that it expanded exponentially. But exactly how much inflation, that might be something that's quantum mechanically uncertain.
I've heard this concept of different histories, different consistent histories of the universe, and that always sounds very confusing. Some would say they were like different alternatives, and we sort of one was chosen. That I sort of understand. But if we say, as many do, that they're all actual, all these different histories of the universe are all actual, we just happen to be in one of the strands and can't access the others. I mean, that sounds bizarre.
I think that's what I more or less believe in. I don't believe in what's called collapse of the wave function down to a single history. I do believe that all of the histories are real. There's a measure to them, so there's sort of a degree of reality. I mean, some of them have what we call very low measure, so in some sense, they don't have much existence, and other ones have more existence.
We have existence. We have good existence, right?
Well, it's not. I mean, of course, for us, I believe that we're selected out by our consciousness, and so it could be if you just looked at the whole universe without focusing on consciousness, it could be that it's a very tiny part of the wave function that has consciousness. But in some sense, when you ask what's observed about the universe, you have to put the selection that there is an observer, that there is observations being made. And once you do that selection, then of course all of the resulting of that does have sentient experiences in it, but of course they can be different. I mean, there might be sentient experiences of seeing the universe being about 14 billion years old as we do, but there might be other sentient experiences of seeing the universe to be significantly younger or significantly older. I mean, some people postulate that there might be Boltzmann brains that they might exist, when in a certain sense the universe is far older than it is today, although most Boltzmann brains would probably not know the age.
It just pops into existence and then pops out of existence, and for that time in existence you don't know the difference between if it's real or not.
Yeah. So it's that there are problems with Boltzmann brains, that we would like to find theories in which they don't, that their contribution is very small compared to ordinary sentient observers. Ordinary observers like us.
We just take the universe as out there in the third-party sense, and we have all these different consistent histories, because of quantum cosmology, because the whole thing was a quantum state, and then how does the state? We think we're in a single state. We don't have any alternatives. We don't see any alternatives. What is the reality of those other states, and is the fact that we're consciousness having made some sort of a selection in a retrospective sense?
Well, I think it would have made a selection to the set that do have sentient observers, but I would believe that even that set is very huge. That there's other sets in which the universe is behaving, significantly differently, but there are sentient observers there. I mean. So I don't see a problem of there being other sentient observers in these other branches any more than I see a problem that I very strongly believe that you are having a sentient experience, and I know from experience that I am. although nothing I say could logically persuade you that that's the case, because from your point of view, you might think I'm just a zombie, and of course the other could be the other way around. But it seems to be a much simpler hypothesis that we're both conscious, and because there's a multitude of different sentient experiences on Earth. It's numerically, of course, a huge extrapolation to have vastly more of them if you had a big number of different histories, what you might call an Everett multiverse, a number of different histories of the universe. It produces a large number of other things, but in some sense it's maybe not qualitatively enormously different from just the large number of sentient observers that we have.
When you're saying large, what do you mean by large? How many is large?
Well, we don't really know. I mean, eternal inflation suggests infinitely many.
No, sure, but those are whole universes or pocket universes, bubble universes.
Now, so for sentient experiments, I don't know how many. I suppose I do tend to think that most probably there's an infinite number of different possible sentient experiences, but maybe probably there's. This is highly guesswork, but you might say that maybe most of the probability or most of the measure is for some finite set of those. I mean, that's plausible, but I can't say I have any evidence, for it or against it. But if it were a finite number, I think it would, I do think it would be utterly huge. I mean, suppose I said 10 to the 100, one followed by 100 zeros after it. Now, I'm not saying it is that at all. Now, it's probably far bigger, but right now I can't.
Probably the exponent.
Yeah, that might be. Yeah, it might be the exponent of that. I don't know exactly even how many sentient experiences there are.
But the point is that quantum theory have given us this just enormous universal possibilities that we've never imagined before.
Right. Yeah, it gives us. Yeah, quantum theory gives us an enormous number of possibilities, and in the Everett view of no collapse, we say that they're all real, and so it says that reality is enormously bigger than what we'd previously thought.